Hello everyone. This is going to be the lecture for section 3.7 in lieu of the class that we missed yesterday, which was September the 8th, due to my illness. In this section, we're going to talk about derivatives of inverse functions. Technically, we're going to talk about how to extend the power rule to rational functions as well, although we've already been talking about derivatives of power functions regardless of the exponent that they have. So that's not going to be particularly relevant to us. Anyway, let's begin by considering a function and its inverse. If f of x is both invertible and differentiable, it seems reasonable that the inverse of f of x is also differentiable. So we have a figure below here that shows the relationship between a function f of x and its inverse f inverse of x. Remember that a function and its inverse are symmetric to one another with respect to the line y equals x. That's why we have the line y equals x here. So if we look at the point A, f inverse of A on the graph of f inverse, having a tangent line with a slope of f inverse prime of A, which is p over q, then this point corresponds to a point f inverse of A on the graph of f of x, having a tangent line with a slope of f prime of f inverse of A, which is q over p in this case. And these are labeled, oh, sorry, I scrolled down there. These are labeled in this diagram. Let's see. Oh. Here and here, right? Thus, if f inverse of x is differentiable at A, then it must be the case that, I suppose these are what I should have been circling, right? Then it must be the case that f inverse prime of A is equal to 1 over f prime of f inverse of A. I created all this on my computer, but I'm using my iPad to record this. So that's why everything's going to be a little bit out of scale at first. And so here we have this inverse function theorem. Let f of x be a function that is both invertible and differentiable. Let y equals f inverse of x be the inverse of f of x. For all x satisfying f inverse or f prime of f inverse of x is not 0, then dy dx is equal to the derivative of f inverse of x, or f inverse prime of x. These are just two interchangeable notations that we see in the middle. And this is 1 over f prime of f inverse of x. Alternatively, if y equals g of x is the inverse of f of x, then g prime of x is equal to 1 over f prime of g of x. I think this is going to be a little bit less complicated than it seems. We just have to find the derivative of the original function, plug its inverse into said derivative, and we just have 1 over that as the derivative of the inverse. Since this is a video, I'm going to move along kind of at my own pace here, but of course if you need some extra time, you can always pause the video to spend some extra time on sections if you need to. So, in this case, we are given the inverse function. In this last definition, we are told that if y equals g of x is the inverse of f of x, then we can use the following formula. So this function is the inverse of some function. So I guess we could just find the inverse of this function to find f of x, right? So to find the inverse of this function, we could set y equals x plus 2 over x. I like to swap the x's and y's here and then solve for y. And we get that y equals 2 over x minus 1. Oh. And so this is my f of x. F of x is 2 over x minus 1. I'm told to use the inverse function theorem to find the derivative of g of x. So if f of x is 2 over x minus 1, like we just found, then g prime of x is equal to 1 over f prime of g of x. So I need to find out what f prime of x is. F prime of x, this is, well, it's not really even a quotient rule problem, right? I don't really have a function over a function. This is, keep in mind that f of x itself, not f prime of x, but f of x itself is really 2 times x minus 1 to the negative 1. So f prime of x is negative 2 times x minus 1 to the negative 2. So f prime of x itself is negative 2 over x minus 1 squared. So g prime of x, since g prime of x is 1 over f prime of g of x, this means that g prime of x is equal to 1 over f prime of g of x is x plus 2 over x this is equal to, let's see, 1 over negative 2 all over x plus 2 over x minus 1 squared. This is equal to x plus 2 over x minus 1 squared all over this negative 2. And I believe that if we work this out completely, if we distribute this, we're going to end up with negative 2 should we just work this out? Yeah, let's work this out. This is going to be I believe this is what we're squaring in the numerator. So we're going to end up with negative 2 over x squared in the long run here. Right? Now, kind of the most important part of this. First, we'll look at this general rule here. This just says that the power rule can be extended to rational exponents. So we kind of have already known this. We've actually been doing this already. So this says that if n is a positive integer, then the derivative of x to the 1 over n is equal to 1 over n times x to the 1 over n minus 1. And if you let n be a positive integer and m be any arbitrary integer, then similarly we can find the derivative of x to the m over n, that's just m over n, times x to the m over n minus 1. So this is just a very simple extension of the power rule. We've actually already done this, but we'll look at a nice and simple example here. Find the equation of the line tangent to the graph of y equals x to the 2/3 at x equals 8. So we can find y prime very easily here. Y prime is 2/3 times x to the negative 1/3. If I want to evaluate this at x equals 8, I could write something like dy dx evaluated at x equals 8 is, this is what I get whenever I plug 8 in. So 2/3 times 8 to the negative 1/3. This is 2/3 times 1 over the cubed root of 8. Oh, there we go. Sorry, I didn't realize this was slightly off screen for a second there. And this is 2/3 times the cubed root of 8 is 2. So this is 2/3 times 1/2, which is 1/3. And this is the slope of the line tangent to the graph at x equals 8. This is not the equation of that line, of course. However, I could also find that if I plug 8 into the original equation, so if I find like f of 8, this is 8 to the 2/3 power, and this is 4. So when x is 8, y is 4. So I have the point 8, 4. I have the slope. So I use my point slope form. Y is equal to 1/3 x minus 8/3 plus 4. This is 1/3 x, and this is going to be plus 4/3. Now, some of the more important stuff here involves derivatives of the inverse trigonometric functions. For instance, if I want to find the derivative of g of x equals sine inverse of x. Now, we'll get more into this later, but another notation for these kinds of functions, so instead of saying sine inverse, you can say arcsine. So arcsine of x is also very common. It's actually preferred. It's a better notation. Oh, I accidentally clicked on error server here. There we go. So we are going to find the derivative of g of x equals sine inverse of x. I think that we can actually kind of reason our way through this one. So let's say that, well, first of all, we should know from 172 that if, say, how do we want to phrase this? If y equals arcsine of x, right? Remember that, again, sine inverse x and arcsine of x are the same thing. This implies that sine of y is equal to x. Now, I can take the derivative of both sides here. I'll do that on another line. I'm going to take the derivative with respect to x of both sides. The derivative of x with respect to x is just 1. The derivative of sine of y with respect to x, well, y itself is a function of x. So I have a cosine of y, and then I have to multiply by the derivative of y with respect to x. Now I want dy dx, right? dy dx is going to end up being my answer here because I'm trying to find the derivative of this function with respect to x. So I can divide both sides by cosine of y here to get that dy dx is equal to 1 over cosine of y. The issue here is I want for this to be a function in terms of x, not a function in terms of y. I know that y is arcsine x. So I need to try to think of a way to rewrite this as a function in terms of x instead of a function in terms of y. I know that y is arcsine x, and I also know that x is sine of y, right? These relationships go together. In order to figure this out, I'm actually going to have to use the Pythagorean identity. Remember that cosine squared theta plus sine squared theta is 1. So, of course, if you change the variables, this is still the same. If I solve for cosine squared, let's see, cosine squared y is 1 minus sine squared y. So logically, this means that cosine y is equal to the square root of this. And the reason why this is going to be useful to us is because x is sine of y. Since x is sine of y, we're going to be able to, once I have this in terms of sine of y, I'm going to be able to rewrite this in terms of x, which is what I want my function to be written in terms of. So I'm going to continue on over here. Dy dx is equal to 1 over the square root of 1 minus sine squared y. And sine of y is x. So dy dx is equal to 1 over the square root of 1 minus x squared. And this is the derivative of arcsine x with respect to x. The derivatives of other inverse trigonometric functions can be derived similarly. And right here, we have a list of all of the derivatives of inverse trigonometric functions. We have arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. Or you could call these like inverse sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, inverse cosecant. And we'll work some examples of problems for these on Monday.